All right, time to get started. All this talk about next quarter makes me sad, because I don't think that we'll have any of you in any class next quarter, which is. That's true. I will have one person in one class.
Wait, what class?
Taking pilots from me.
I've read it, but I haven't seen it.
So, yeah, where are we in the class? We've recently taken an exam. We don't have to worry quite yet about the next exam. We have an assignment due tomorrow. That is the stacks and queues and postfix. I will be revealing a new assignment probably today to do with hashing. And I will at least start having that due next Wednesday. I don't know yet. We'll see how that goes. I remain a little bit open to pushing that back if the rest of the quarter lines up. Make sure that we can finish everything that I am planning to finish within the quarter. But in the meantime, we have to finish talking about hashing so that you can do the homework. We started talking about collisions, or this, what happens when we're mapping two elements to the same index in the array that is storing this hash table. So how do we deal with that? We came up with a couple of ideas. Well, I think we came up with one idea. And that idea was to make each index of that array the head of a linked list. And then we store everything in that maps to that index in that linked list. What that does is it doesn't really affect the actual complexity, but it divides it by a huge constant factor, the size of the array, which is usually a massive improvement. So downsides can store the most one element in a given index if we store this as an array and not an array of objects. So maybe same index, we said that using a quadratic amount of memory was infeasible. We have a collision, we need to handle it. So we're going to look at the other solution that doesn't involve taking this and making each index the head of a linked list. So linear probing is a way to just store the array as a series of the objects that we're trying to store without it being itself another object, a linked list. So we still want to just store one element at a particular index. So linear probing basically says, okay, we have a collision, we're just going to look at the next index. And now, instead of searching through the entire array, the value from the hash function maps to the first place that we would look. And then we start looking from there linearly on. And the idea is if this array isn't super full, we will be finding what is stored there much more efficiently. And as the array is closer and closer to empty, we get closer and closer to a constant time search. So a constant time get and a constant time store. As the array gets fuller and fuller, then it becomes closer and closer to a linear time based on the size of the hash table, because every element is going to be full. And if we're trying to map something to somewhere and that's full, and the next element is full, and the next element is full, and the next element is full, we loop back around, that element's full, and the next element is full, and the next element is full. It could be that we're looking for one empty spot to store something. And if that were the case, then this turns into a linear search. So with linear probing, we're just going to look at the next index and continue this process, loop it until we find an empty index to store that data. What do we think? Pros and cons of this approach? Well, we talked about the complexity of it. So depending on if the array is empty or full, any other pros and cons we can think of? We already talked about that. Yeah.
Once it's completely full, there's nowhere to put the element, right?
Yeah. So what's done in practice is we will declare a new larger array, take everything from the original and rehash it into the new table size. And that becomes an expensive operation, but it's only something we have to do whenever the table reaches a critical mass of full. In fact, we don't even wait for it to be full. We come up with a percentage full that we can we decide is the maximum allowable before it starts affecting our performance, and then we resize and rehash. Great point, though. There is one other major problem with linear probing that we need to identify and find. It's a little bit difficult to see, but just thinking about all of the ways that you could use this system. What are we doing with it? We're adding to it, we're getting from it, we're removing elements from it. What added complexity or what added issue arises when we try to remove from this? Yeah, we actually don't know. Let's say we find an empty slot. Does that empty slot, we're searching for it, we find an empty slot. Does that mean it's not in the array? Not necessarily. That's what makes this so difficult. I can draw this out because I think this is a very important thing to visualize. I'm going to use a very small array to do this because it doesn't need to be large. But let's say we have a 4-element array, indices 0, 1, 2, and 3. We want to hash some value that maps to index 2. So unfortunately, index 2 already has some junk in it. I'm going to call this 13. There's 13 here, there's 13 here, there's something blank here. And then there's our, let's say there's something here, doesn't matter. But we want to hash the value 8, and it wants to hash to index 2 for some reason. We see this is here, we see this is here, we see this is here, we see this is empty. Great, we're going to put 8 here. When we hash to go remove 8, we're still going to hash into index 2, so we're going to start searching for it. This would work. But let's say that the thing we do before we try to remove 8 is we want to remove one of these elements. So we hash 13, we remove 13 from the array. The 8 is still there. And in fact, when we start looking at 2, the very first thing we're going to see is a blank cell. So unfortunately, this does not tell us that this is not in the array. So this is something that we need to be able to handle or come up with some intelligent way to do this, because we don't want, once we've used this hash table for a while, every remove is going to become linear in nature. We just don't know where it's going to be, if it's going to be there. So we don't want remove to be linear. And in fact, there are things we can do about this. Does anyone have any ideas? How would you handle this? This blank should mean something. Already done all of this work. Here's something similar to what I've done. There are actually a couple of options that we have, and we'll talk about that here in a second, but keep that in the back of your mind, as this is an issue, and this is an issue that we need to solve in order for this structure to be better at removing things than just an array or any other kind of list. So linear probing code looks something like this. We set a table size M, so this is an array size of 30,001, which is a nice prime number. We will store all of our values, all of our keys. When we hash a particular key, we get a hash value for it. Then we can put a key with an associated hash value into the hash table with that particular index that is derived from hashing and then modding, which is what we see in the get. So put is also here just on the next slide. So get just says if we want to figure out where it is in the table, we need to hash its value. We're gonna look at that hash value mod m to try to find it, and if we don't find it, we're going to continue to increment, 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 increment until we find it. Has the same issues that we just talked about. If the table is full, this is gonna take a while. But looks something like this. We want to place something new into the table. We're going to hash it. Then we're just going to look and continue looping until we find some place that is empty. Keys of I should be null. Once that happens, we can put it in there. Here's an example of the removal problem. So we are going to attempt to delete S. Can anyone describe what's happening here? Exactly what I was describing, but. So something like we want to determine whether H is in the table. But before doing that, we delete S. So S maps directly to index 6. So when we go to delete S, or I guess, yeah, delete 0. We map the key, S maps to 6, so we delete this whole thing, it's gone. But now H maps to 4. So we start looking for H here. Is this it? Is this it? Is this it? And we see that blank. And it is in the table, it's just in the very next cell. But because we deleted something before it, we don't know that, and that blank doesn't actually tell us anything. So we have no choice but to look through the entire array to try to find something. Since there's no guarantee that if we reach a blank cell that it's not in the table, and we'd like to be able to stop this sooner. Anyone come up with any solutions? What could we do? Let's talk about our options. So the first one is to introduce what we're going to call a tombstone. This is just an aspect of the object that's going to be stored in the value field. And so it's now going to be a tuple of the object and this flag. This flag tells us either something used to be here and was deleted, or this cell has been blank since this hash table was created. How does that answer this question for us, or tell us whether we should keep searching or not? Imagine nothing has ever been there. So this tombstone flag is false. What does that tell us?
You don't need to keep searching.
We don't need to keep searching because we can't have deleted something from there. In order to add something at an index after that, that would have had to be full at the time that we tried to insert the thing we're looking to remove. If that were the case, then we would need to keep looking, but since the flag is false, it is now impossible for the thing that we are looking for to be anywhere past that in the array. Does that make sense? So if we, back here, we're looking for a particular Boolean flag here. In this case, that flag would be true because this used to be there, which would say, yes, something was here. It is possible that when we added this H, this S, or this thing that was here that made this flag true when we deleted it, we could have inserted after that. So we need to keep looking. On the other hand, if this is false, this says that there was nothing here ever. If that were the case, when we inserted H, the last place we could have inserted it was at this place. Since it is not there, it is nowhere. It's not in the table. So you just add this field to every element of the array. And of course, this array is now, if it wasn't before, it's now an array of objects. Where those objects have fields. One of the fields is whatever object it's supposed to be storing, and one of the fields is this tombstone. So how do we manipulate the tombstone with linear probing? For insertion, the tombstone is empty, it's an empty element that can be filled. So when we insert, if we come upon a blank, and that blank has a tombstone that is false, we're going to insert there and turn the tombstone to true. When we delete, I guess we wait to set the tombstone flag to true until we delete, sorry. When we delete, we remove the element and we set the flag to true. And that way, it really doesn't matter when you do it. It's going to be true regardless. And the only time you'd be asking this question would be when it's empty. But we remove the element, set the tombstone flag to true, and that tells us now whether we should keep looking or not when we are searching for something and come upon this empty cell. How does contains work? If you're looking for an element, you're doing a get for a particular element or it contains. If we do see a tombstone on an empty index, then, sorry, if you do not, I can't even read my own slide. If you don't see a tombstone, then you stop looking. And that just means that nothing used to be there, just like with the removal. So it can't be in the rest of the array. However, if it is, then we do still have to keep looking. So this is the equivalent of just an element that doesn't match the query. You have to keep looking. Questions on any of this so far?
Maybe I'll like get practice with this.
Yeah.
Okay.
Yeah, I drew it out a little bit right before you walked in, unfortunately. It's not good. Yeah,
We always add at the first index, we never add that indexes on the response.
so you add, the very first thing is added wherever it hashes. So if it hashes to index 7, then you would put it at index 7. And there'd be nothing at index 0, 1, 2, 3, 4, 5, 6, and something at index 7.
So if the tombstone flags are false in those first indexes, but you want to find them in 7.
Yeah. So the first element, the first place you look is wherever it hashes. So if you're trying to find that element, you rehash again and say, if I didn't store this, it would have been at index 7. So then you look at index 7 is where you begin. So indices 0 through 6 are the last places you would look after you get to the very end of the array if you're still trying to search for it. That is a great point, though. Yeah, you start looking at that hash value.
What was the value starting with right there?
So that is slightly confusing. This is treating this hash more like a map because so there are two different types of hash. There's just a hash table, which we're talking about, but there's also a hash map that maps keys to values. We'll actually talk about maps a little bit later, but I'll give you the brief overview of what a map is. A map is it's the equivalent of a Python dictionary, if you've seen that before, but it's a mapping of keys to values. The key list is just a set, and then the values are whatever we're linking that to. So there's some kind of either cause and effect or linking between these two elements. This key maps to this particular value. So it could be something like states to state capitals. And that way the key is a state, but it would also be possible to have duplicate names of capitals of states. But they would be unique on the identifier. The identifier being the state. Given a state, identify its capital, and not necessarily vice versa. So the states would be a set, and then the map, the actual values that link to that would be something that has to do with that.
So then that was a hash map, not a table.
Yeah, that was technically a hash map and not just a hash table. A hash table will just store the value without the key.
Right, and you use just the indices.
Yeah, the key is the index
Right.
that the hash gets to. Yeah, that is a good point. Any other questions? Yeah,
So with the hash table, the benefit is the searching.
yeah, you are trying to minimize the cost of the put the cost of the contains, the cost of the remove. You want to minimize that because they're all going to be linear if you use an underlying list. And at least with this, now we think that it's going to be closer to constant if the table is relatively empty. So if you make a 30,001 hash table for 1,000 elements, it's going to work really well. How many searches would you have to do on average? That's a good math question. You have 30,000 elements, put plate to 30,000 bins, and you have 1,000 balls you're going to randomly toss into those 30,000 bins. If you're trying to look for a particular element, how many times do you think you would have to move to the next element? Not particularly frequently. It's only 1/30th full, about 3% full, and some of those will have, by chance, have gone in the same bin. So even if they did, we had an equal distribution of once there was a ball in a bin, there was nothing else. It'd just be about a 3% chance that you'd have to look at the next element to try to find it. So you find it right where you're looking for it 97% of the time. So we're saving a lot of time by using an array that's way larger than we need to store 1,000 elements. So that's that space-time trade-off we were talking about yesterday. A lot more memory is needed, but it reduces the complexity of actually finding it. When do we resize? We should probably answer that question. So we know as the table fills, it gets closer and closer to a linear complexity. Store a single value. Now, if we had a 30,000 size table and we had 30,000 elements in it, then we have no idea how much work we're doing to try to find it. We might as well not have done this process and just used a regular list that we added at the end whenever there was a new element, because it's going to take us that long to determine if something's in the table or to remove something that we think is in the table. And we couldn't add anything new to the table because it's full. Or assume that there's one element missing. Adding and finding that location is still going to be linear with respect to the size of the table. What's nice, though, is that resizing the entire table is a single linear time operation. So all we're going to do is described earlier, we're going to make a new array that is twice the size of the old one, and we're going to rehash everything that was in the table, the old table, into the new table. And that will say that if it was absolutely full, now it is 50% full. But when do we want to do that? When is the best time to grow and shrink the table? We don't want to get to the point where the table is full, because then it is actually a linear time operation. But where is that difference between when the table was 3% full, almost all of the time, it was right there. And if it wasn't right there, then it was very likely to be at the very next index. Unless we got super unlucky, if they somehow all mapped to exactly the same cell, there would be 1,000 consecutive cells filled and 29,000 empty. And then again, it would still be exactly like a list, but that is incredibly unlikely. So unlikely that I would bet my life on that not happening. That's how sure I am that that wouldn't be the case, unless you wrangled the data to do exactly that. Assuming this is random data, it is so unlikely. So what do we think? Where is that boundary between something that's linear time and something that is technically constant? Yeah,
75% capacity.
75% capacity. Let's do the math on half full. When the table is half full, how many searches on average will we need? This is not worst case, but in the average case, the table is half full. Every other element is full on average. We'll probably find exactly what we're looking for about half the time. It will take a little bit longer than 2, about a quarter of the time. But the average, as we will see, is exactly 2 operations. So when it's half full, it's constant. When the table is 1/8 or less full, you can cut the table size in half, and it's still constant. Because of the new one, it'll still be a quarter full, which gives it room to grow to be half full. You don't wanna cut the table in half, and then the very next thing you do is an add, and that causes it to grow, and the very next thing you do is a remove, and that causes it to shrink. You want there to be distance between when you wanna resize the table bigger and resize the table smaller, so you don't get caught in that back and forth linear time operation, add, remove, add, remove, add, remove. So an eighth or less full tells us for the trigger of we can make this array smaller and not affect the complexity, even with significantly more adds at the end of it. So of course, we have to rehash all the keys when we do this because the table size has changed. When we mod by that table size, the index also changes. Does that make sense? Yeah,
So this time complexity for when we're retrieving elements is for when we have a hash table that has or has dealt with collisions.
yeah, this is all for linear probing.
Okay.
So, of course, that's what makes it a linear time operation. We have to rehash everything. But is it intuitive that when you mod by the table size and the table size changes, the index that you want to store it at changes? Giving you an example, let's say the value I'm trying to hash is 89. The table size is currently 20. No, it's not gonna work. Table size is currently 30. Where would it hash? 89 mod 30? 29, that is right. So you want to store it at index 29, but let's say now that causes it to be so full that we need to rehash everything. So we go from a table size of 30 to a table size of 60. What is 89 mod 60? That is 29 again, that's annoying. This is why we use prime size tables, by the way. This is exactly why we use prime size tables. So 89 mod 7. Yeah, so that goes in and gives us 12 times 7 is 84. So it gives us 5. If you double it, now instead of just doubling it, double it and find the prime that is just above that. So instead of going from 7 to 14, go from 7 to 14, what's the next prime above 14? 17? What is 89 mod 17? A little harder. 17, 34, 68, 75, 82, 89, which means 0. I'm going 17. Yeah, I think you're right. So it is a different spot when you do that. So using prime size tables helps a lot in making sure that when you double it, if you're using something that's a nice, easy number in base 10, when you double it, it actually may hash to exactly that same spot.
Is there a way to quickly so we get the next certain number?
I've written that in a fun side exercise in 212. The answer is you do need a prime generator, but yes, you can do that relatively easy with just a prime generator. So final thoughts on this concept of linear probing. So the issue that we see when we actually do this in practice is what we call clustering. This means that even if your data is randomly distributed in what hash it ends up hashing, what index it ends up hashing to, we see clustering where there's a bunch of hashes that are, a bunch of data that's stored right next to each other. Can anyone think of the intuition for why that would be the case, even in randomly distributed data? Well, let's do it with a small array. I think you're on the right track here. 2, 3, 4, nice and small. We have a nice 5-element array. So I'm going to hash the very first number and 4 hashes to index 3. Now, the next number. How many places can it be stored? 4 places, either here, here, not here, or here. What is the likelihood that we hash into 0? It is not. Why? Yeah.
There's a collision.
Yeah, it could map here or here with equal likelihood, right? And if it maps here or here, if the hash says that it's supposed to hash to index 3 or index 4, it's gonna get stored in index 4. Because of that collision. So it is more likely that we create this cluster right here than it is that we separate it. And this just gets worse and worse the more full the table gets, and the larger this cluster becomes. This starts to map more and more frequently to the next element after that cluster with more and more likelihood. So that clustering just becomes worse and worse the more you add to it. But I think it's easier to visualize with a smaller example like this as to why it's not equally likely to be at any of these positions. Make sense? Any questions about that? So that's the big downside of linear probing in practice, is we see clustering. You end up more likely to hash to that next element after that cluster, because anywhere in that cluster will map to that next element after that cluster. So in practice, we get things that look kind of like this. So lots of potential values would map into the cluster, which tells us that it's very likely that this is the next cell that gets filled. The next most likely place is going to be here. So what's another solution to this? Separate chaining, or the concept of chaining, we actually already talked about this. Replace each array index with a linked list. When we find a collision, now rather than looking at the next index, we're going to add the new element at the front of the linked list that exists at that index. So we never need to look at any other index except where this value would hash. This seems like it's just a better solution the first time you look at it, but it's worth thinking about what are the downsides. In what ways is this worse than linear probing? Yeah,
Potentially doing a get, so say you have a really long linked list and you want to get at the very end of it, you have to go all the way
Yeah.
through to the end.
well, with linear probing, you would also probably have to do some things, and all of those would map there as well. You may have to do a significant amount of searching to find it as well. So it is a downside, but I think it's a downside that it shares with linear probing. Really good idea, though. Is there any downside this has above and beyond what linear probing has?
A lot of space.
Yes, that's the big one, is it takes a lot more memory. The table is the cap of how much memory you're going to have. When each one of those is the head of a linked list that can now be arbitrarily long, you're actually multiplying your memory as this table would have gotten fuller and fuller. On the other hand, it is faster. It saves time. So once again, we get a time versus memory trade-off. If time is super important, then linear probing is actually faster, as long as you're resizing your table at the right times. Once the table gets half full or more than half full, rehash. Once the table gets less than an eighth full, rehash. If time is important, then if time is important, then you go here. If memory is important, then you use linear probing. Like I said that backwards when I first said that. But this has it right. There are other ideas that float around out there that you might see, not that are frequently used in practice. These are the two most frequently used in practice, either linear probing or separate chaining. Although if you want to get around the clustering of linear probing, there are some similar ideas to linear probing that can minimize that clustering. So the first one of those is called a two-probe hash. You hash to two locations. So you come up with two separate hash functions. Every possible object has two separate hash functions. You look at both locations that it would hash, and you look at the number of places you have to look to be able to store it. And you take the minimum of those two and you store it there. The expected longest chain that you would have in your table goes from log n to the log of n if you do that, which is a pretty significant improvement. So that's called a two-probe hash. There's called a double hash, where you use linear probing, but you have some predetermined sequence that is not linear that resolves the collision. So one of these is called quadratic probing, and it uses all of the square numbers, 1, 4, 9, 16, etc. And now when you hash to, let's say, index 4, the first place you try to look is index 4. Then you look at 4 plus 1 mod the table size. Then you look at 4 plus 4 mod the table size. Then you look at 4 plus 9 mod the table size. 4 plus 16 mod the table size. So this, in practice, mostly eliminates that clustering because you're not looking at sequences that are right next to each other. And since that sequence, that value is always increasing in size compared to the last one, it doesn't have that clustering effect when you try to hash to different locations. And that means as well that because you're not expecting as much clustering, that you can allow it to become more than half full before you need to resize. So in practice, you get closer to what was suggested earlier, more like the 75% full before you really need to resize the table. This seems like a lot of fun and good until you try to delete. Deletion gets a little bit harder. Because now you see a tombstone at that location, and when was that tombstone left? Was it left? When you map to different locations, it might be the +4 that gets you there, and from some other location, it's the +9 that gets there. So the next one would be a +9 from there or a +16 from there. Those are different locations, so that tombstone actually doesn't tell us anything. So let's actually walk through an example of this, because I think just going through and seeing this whole process is useful. So we're going to start with an array of size 7, nice prime number. We're going to use linear probing to handle, and you're going to insert the following numbers. So let's start there. Insert 10 and then 1 and then 8 and then 15 and then 14. And for your hash, these are just integers. You're going to take that integer and mod the table size, and that's going to tell you the index where you want to store it. Feel free to work on your own, work with people around you. But let's see what this looks like in practice.
Rewriting, do the code or drawing it out?
No, it's drawing it out.
Okay.
We can do the first one together to get you started. Where does 10 hash? 3? Why? Mod 7? 10 mod 7 is 3? Anyone stuck on the modular arithmetic? Is that something we've all seen before and know how to do off the top of our heads? Yeah, so 10 mod 7 is the remainder when you divide it by 7. 10 divided by 7 is 1 remainder 3. Going back to like our last, what, third, fourth grade, the last time we used a remainder for anything remotely productive. And computer scientists actually use it and care about it all the time. Well, we need to store it somewhere. We're basically making a list that contains these data elements. But rather than just storing them in a list, if we did that, then it would take linear amounts of time to search for things. If we hash them like this, then we say, does this table contain 10? If it does, by doing this, we can now say 10 mod 7 is 3. If 10 is in the table, it's going to be at index 3. So much faster. Rather than searching through the whole list, it's going to be right at 3 unless there's a collision. Yeah. What's the next one? What's the next one? What index do we map to? 1. 1 mod 7 is 1. We're going to store 1 at index 1. How about 8? Also maps to 1. What are we going to do about it?
2.
We're just going to move to the next one and store it there. How about 15? Also maps to 1. So can 15 go here? No. Can 15 go here? No. Can 15 go here? No. 15 is going to go here. We start to see that clustering at work, even though these are kind of strange data points. What about 14? Where does that go?
0.
0. Luckily, that's right where we're looking for it. Great. So we are not resizing this table. Probably should have by now, but aside from the point. So now let's trace contains on 15. How does a contains method work on 15? What's the first step? Yeah, so we hash it. 15 mod 7 is 1, so we're going to look here. We see something. It's not 15. We look here. We see something. It's not 15. We look here. We see something. It's not 15. We look here. We see something. It is 15. Contains for this exact example doesn't look particularly efficient. And that is because of the clustering that we saw and the fact that we should have resized this table before now.
So 21, actually search all the way to
It's like you read my mind. Trace contains on 21, something that's not in the array. So we want to return either true or false, 21 is in this or not. We would want to hash the 21, get 0. No, 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 no. Now we see this 5, and this 5 does not have a tombstone. So that tells us that it's not on the table, we don't have to look elsewhere. Okay. Let's delete 1. So to delete 1, we hash it, goes to index 1, and we remove it. And when we remove it, we make this nice little tombstone. I don't know, something like that. So we add a little tombstone that says there used to be something here, but we slaughtered it mercilessly. So what do we think about? How does this affect future contains calls? Because we have other elements in here that did hash to 1, right? 8 hashed to 1. 15 hashed to 1. So there are some contains where we want to make sure that we can access and return true that this hash table contains that. So it's very important that we put that tombstone there, because that tells us continue looking, rather than what we saw when we were looking for 21, we saw this 5 without a tombstone that said, you're done. It's guaranteed to not be in the field. Yeah.
So when you resize, that if there's like tombstones.
It does clear all your tombstones. Yeah, yeah. Now the last few bits of repeat this with separate chaining now instead of linear probing. So what changes now when we have separate chaining? What does this look like when we use linked lists instead of just an array of integers? Yeah,
So if there's one that matches to the same index, would it just be
Yeah.
added as a?
added as a node. And in fact, it gets added as the head is what I said. It's probably easier to add it as the tail if I'm drawing it on the board. There's something to be said about something that was inserted most recently might be the most likely thing to be interacted with, which is why you would insert it at the head rather than the tail. If whatever had been in the table the longest was most likely to be contains call or dot or something else, then you would want to insert it at the tail so that the whatever had been in the table the longest was at the head. So that might be application dependent as well, but that's a design decision that you would need to make when you design a particular hash table for a particular problem. Yeah,
So when you, I mean, in code, you start at the key, so like the key, which would be the hashed
yeah,
value. Then you look there.
Yeah.
And you look at it.
yeah,
Instead of just starting at 0.
correct.
And that's what.
Yeah, that's why it's significantly more efficient. Exactly. So it's still gonna look exactly like this, except now, instead of each of these values being. We're going to have these as the head of a linked list, and this is why. You would want to implement a linked list with a dummy head. Because we don't want the first value that we see here to be an actual value necessarily, but it could just be a reference to the start of a linked list, and that way we can declare all of these initially to just be null. So we can instantiate all of these linked lists without adding a value to them and start checking whether this particular element is null. That element will always be there, but now when you look at its next, that is null. So first, we wanted to insert 10, that mapped to index 3. So we're going to make, and I'm going to draw this vertically instead of horizontally. We're going to add a value of 10 and a next of null. I'm not going to draw the X because we might need to do something with that. I don't want to erase it. So this now points to a linked node, data 10, next null. Inserting the 1, that goes here. And I am adding at the tail, even though my slide said add at the head. Easier to draw. I'm gonna run into my text here momentarily. Then we wanted to do 8, that also maps to index 1. So instead of doing any probing whatsoever, we're just going to say this points to the next linked node that has data 8 and next null. And now I can add this as an arrow. Then we wanted to do 15. 15 also maps to 1. So we're going to add 15. And I think now we're finally done with this, because 14 maps to 0. 14 and null and null. So that becomes what our hash table looks like visually after we do this. So again, tracing contains on 15. Instead of having to go through all of this work, you can see that 15 is 3 away instead of 1, 2, 3, 4 away. So it's a little bit faster to find that 15. When we want to trace contains on 21, 21 maps to 0, and now instead of doing 1, 2, 3, 4, 5, 6 checks, we do 1, done. Much faster to figure out that something is not on the table. Of course, the downside is this memory is this memory. This is all excess memory, and you can imagine as this table grows in size and we add more and more to it, that the memory gets worse and worse proportionally compared to just the linear probing is storing a lot less data. But when you store less data, there's more work that you need to do to answer the same question. Questions on this example? All right, we will come back and finish this off. This is literally the last element. This is the last thing in this slide deck right here. What's faster and what's slower? Faster, more memory, slower, less memory.
When you're deleting Oh, I answered it in my head.
Yeah, in delete something like this, is that your question?
God, you just like have the pointer, yeah.
Yeah, it's a delete from a linked list, it's exactly the same, there's no previous.
So you don't have any like two steps or anything, it's just gone.
Yeah.
The garbage is like, read it.
Yeah.
Yeah, I understand.
Yeah.
Already got it out.
Awesome.
Why would that happen?
Right? Stacks can only use these options, you have been removing everything from the stack to look for something and then put it back on. And that would not be particularly effective work. Yeah, that's-